Maybe we can start now, and I will give a short introduction to Jamie. Jamie Tucker-Foltz is a fifth-year PhD student at Harvard University, advised by Ariel Procascia, and he's supported by a Google PhD fellowship and an NSF graduate research fellowship. His research focuses on applying techniques from theoretical computer science to improve political and economic institutions. And he works on a range of topics in fair division, social choice theory, and algorithmic game theory. And he's especially interested in algorithms for field redistricting and gerrymandering detection. And he also has interest in descriptive complexity, computational topology, and graph theory. So maybe let's welcome Jamie.
Great. Hi, everyone. Thank you all for coming. This is definitely the biggest time zone shift I've ever presented at. Yoram just told me that this is very early for you guys, and I assure you it's just as late over here, so literally. But yeah, I'm very excited, and thank you for inviting me. So I'm going to be talking about two papers mostly that are very similar models. One was in EC this last year, and one was in AAAI the previous year. And they're all about this question of how do you aggregate preferences with limited access to information of the people that you're trying to aggregate the preferences over. Okay, and so this falls within a research area called social choice theory. And as I said in the abstract, I don't want to assume anyone knows what social choice theory is. So I'll just give you the one slide highlights of what social choice theory is typically thought of as. And it's usually thought of in the context of voting in elections. So you have n voters, m candidates, and the input to your problem is some complete description of all the preferences of all the voters over all of the candidates. So you can think of that as some table where I say how many voters ranked B as their first choice, C as their second choice, A as their third choice. So there's two people that have that ranking, one person is this ranking, etc. And from this input preferences, you have to aggregate them into social preferences. So this is called social choice theory. And often one of the most common frameworks for that is just finding a single winner. So that's called a voting rule. A voting rule takes as input this ranked information and outputs a winner. Say maybe some voting rule says, I think A should be the winner here. And so this was inaugurated by Kenneth Arrow in his very famous paper in 1950 and he said, we ask if it is formally possible to construct a procedure for passing from a set of known individual tastes to a pattern of social decision making. And the sort of the most popular thing that's been studied is this context of voting in election, where the candidates are real people submit ballots, and then we're talking about what is the best voting rule that satisfies some axiomatic properties. Which ones can we satisfy together? Which ones we can't? That's sort of classic social choice theory. And in this talk, I really want to go back to this vision that of the wide net that Arrow casts in this quote here, where we're not just talking about voting, but we're talking about patterns of social decision making, and more broadly, how do we aggregate individual preferences into societal preferences? And this can be done in the simple context where you've got a list of ballots in front of you and you need to figure out who wins, or more complicated contexts as well. And an example that we're going to take as motivating this work is this the emergence of these platforms. This is a platform called Polis. The website is pol.is, and it is sort of an online platform meant to facilitate deliberation and democratic decision making. And these I have a bunch of screenshots from Polis because it fits pretty nicely with the model I'm going to be talking about. And this is sort of their big flow chart of how do they make a decision about an issue. And so one case study that Polis likes to brag about is that they were contracted by the government of Taiwan to try to gauge public opinions about the regulation of rideshare apps. And so they had this huge process for gathering the inputs from various stakeholders and just the general public. And so that's this phase of the online deliberation phase. And the individual users would arrive to the platform and they'd be allowed to write free-form text of some opinion that they have about the issue. Okay, and so in this case study, it was about how Uber and ride-sharing apps should be regulated. And then these comments then get shown to other users via this comment routing algorithm, and then they can either approve or disapprove of the comment or pass. And of course, not everyone is going to be able to see every comment here. Okay, so you can think of this as just this phase, this deliberation phase. And so what the algorithm then outputs is it wants to like come up with a summary to present to the decision-making bodies, like the legislature, and say, okay, this is how people think. And so this is a preference aggregation task of trying to summarize these different opinions and who approves of what into like some like clean set of like here's the nice summary of what the social preferences are. All right, and so that's just this phase here that I'm going to be focusing on, this online deliberation and comment curation phase, because that's the most similar to the social choice theory framework. And this is a blow up again from the Polis white papers of just this phase of finding a selection of comments to present as like here this encapsulates the social preferences. They do all these steps. The main parts of it is they have this comment routing algorithm that figures out which comments to show to which individuals, and from that they get more data that tells them like, do you approve this comment, do you approve that comment, and then they cluster it, and they do this dimension reduction algorithm, and then it's this complicated algorithm that feeds back into their comment routing algorithm, and eventually they end up with, here are the set of comments that fully describe society to the best that we could come up with. All right, so this is just one example of a more complicated process of making decisions. And it kind of shows how aggregating preferences is harder. So here, the candidates are not like a small set of individual people, but they're every possible political opinion you might have, or at least all the ones that were submitted to the platform. But any possible text opinion is a candidate in this space. And so you're not going to be able to get these full preferences of every individual over every candidate. That's like asking every person that's participating in this huge platform to rank or approve of everything that everyone could have possibly said. And so you're not going to get that information. You're in this limited information environment. What can you do? Okay, so that's the sort of motivation for this talk. And now, any questions before I dive into the sort of model? Please, anytime throughout this, just unmute yourselves. I won't see if there's like raised hands or anything. So please just interrupt me if you have any questions. I want to make sure everyone is following. Thank you. Okay. So here's how we're going to model this problem. And we're going to assume that there is some underlying ground truth distribution D of the voter preferences. Okay, so this is like one of those tables that describes how many people have each type of preference. And then this is unknown to the algorithm that's trying to aggregate these preferences. Instead, they can submit queries. And so the basic, most simple model is kind of what happens on a platform like Polis. A random voter arrives, and so that's like sampling a ranked order or approval order from this distribution D. And then you can ask the voter about any set S of at most T of the M alternative. So M is going to be some really big number. T is going to be some small number. Like maybe you get lucky and someone will answer like 10 questions or rank 10 candidates. And then the voter leaves and may never come back. Okay, so that's one query. You get to query a random voter from the distribution and ask what is their preference. And note that the key feature of this is that because the voter never necessarily comes back, it's never going to be possible to make sure you get information about preferences over more than T alternatives. You can't like make multiple queries and from that overlapping information, you get a full description of any one voter's preferences. It's a totally random individual each time. Okay, so that's just a key thing. A lot of people are confused, like, oh, why, if I want to know how you rank A, B, and C, why can't I ask you about A and B, and then ask you about B and C, and then ask you about A and C? Well, they're different people that would be asked that question each time. Okay.
May I ask a question?
Yes.
So will you know the type of voter when it arrives?
No,
like
the voters
you will know. So they're totally random, and you will never know whether they're from the same type or.
We don't think of them as types. We think of them just as individuals. Everyone is an anonymous person with an equally weighted opinion.
Oh, I see.
Yeah.
I just thought that if you can know that this person and that person are from the same time, then they share the same preference, and you can utilize this information to know more about more than T alternatives through multiple queries.
If your definition of type is that like the complete specification of the preferences, yeah, you're never going to be able to learn anyone's type. So you're only if someone's type is they rank A above B above C in the ranking context, You can query them about, say, maybe A and B, but not A, B, and C. You never learn what their full type is. You just learn some partial information about it.
Okay, I see.
And you never know that you're going to, yeah. So that's what I'm going to call noisy query. And that's actually not going to be the focus. We're going to sort of abstract this into an idealized query, which we call an exact query. And this is going to be the focus of the talk. I'm not going to really talk about noisy query model much because it's just it's an approximation of exact queries. And an exact query says the algorithm can ask about some set of T alternatives and then instantly learns the distribution D restricted to that set S. So this is something that you could simulate with a bunch of noisy queries. Namely, you have some set S they want to do an exact query on. You make a bunch of noisy queries and get some empirical distribution. We're assuming these voters are IID sampled from D, and so then we take that to be the distribution of D restricted to that set S. So and there'll be an approximation of the underlying true distribution. An exact query, we're giving you more power and you just learn it exactly. So this is more powerful than noisy queries. You can, with a bunch of noisy queries, you can almost get an exact query, and it's an approximation of it. So this is a strictly more powerful type of query. And most of the results I'm talking about today are lower bounds against exact queries, things you can't do with exact queries. There are also going to be some positive results, things you can do. And in that case, again, the recipe is just simulated with a bunch of noisy queries. But the problem is much more mathematically clean to talk about exact queries. Okay, and so I've been kind of flip-flopping between, okay, so let me say, like, what are the main questions first? So the main questions we're going to ask are, first, the information-theoretic question. What voting rules can be implemented with a small query size? What types of classic social choice theory preference aggregation tasks can you do with a smaller T than M, the number of candidates? Then there's a computational question of when you can do that, how many queries do you need? Okay, so that's a sort of second question. And then finally, there's a question about the model, which is, does it help to ask these queries adaptively? Can you condition your subsequent queries on the early responses you get? And this is a very interesting practical question. If you think about Polis, for example, is that they have this comment routing step of their algorithm, and that's a sort of adaptive thing where they can take feedback from previous queries responses they get, learn some voters' preferences that'll inform their comment routing algorithm of who they show comments to other voters, and that's sort of like using that information to design your future queries. And so the question is, like, do you really need this? Does it help to have an adaptive algorithm? Okay, so these are the three typical questions, and we're going to ask these questions in two different contexts. And both of these are very well studied in social choice theory. The first is ranking, which is what I started with in my initial example, where you've got a bunch of ranked preferences, and when you do a query restricted to a subset, you get the restriction of that total order of the candidates to some subset of candidates. And so this was a paper that was in EC 2024 this year, is with my collaborators Daniel Halpern and Safwan Hussain, and so yeah, and I'm going to start with that one because I think that's actually like the more basic, classically studied thing in social choice theory. And then I'm going to talk about this also. I'll spend most of the time on this first one, but I'll also talk about an earlier paper that was the same thing, but with approval ballots and committee selection. And so this is another task in social choice theory where the input is actually of the form that you get in Polis. Like in Polis, people don't submit rankings. They submit who do you approve of and who do you disapprove of. And so that's known as approval ballots in social choice theory. And there, the interesting question is, okay, selecting one winner is kind of trivial. You should select the person that is approved most, but that's not actually what Polis wants to do. The Polis wants to solve the harder problem of selecting some set K of the comments. And then there's a bunch of classic axioms about how you should select those K comments. And we ask similar questions. Can you do that with a limited query size? And that was joint work with, again, Daniel Halpern, Greg Keeney, my advisor, Ariel Procaccia, and Manuel Wuthridge. Okay, so that's where we're going. I'm going to jump into the ranked preferences now. Okay, so let me start with an example of a rule that we can compute with a very small query size, and that's called the Borda count. And so this is a voting rule. This selects a winning candidate from the list of complete preferences, and it assigns m minus j points to each voter's jth choice, and then selects the candidate with the highest total score. Okay, so in this little example from earlier, we can compute the Borda scores of each of the candidates. We say, okay, these two voters prefer B, then C, then A. So B is going to get 2 points for each of these voters, so 4 points total, 1 point for each of these voters, just 2 points. So yeah, and basically this first row, I multiply all the candidate votes by 2. The second row I multiply by 1. Third row don't get anything. So what's the Borda score of A here? Well, A gets 2 points for each of these voters. So that's 3 times 2. It gets 1 point for these voters and 1 point for these voters. So their total Borda score is 10. Okay. And as you can do a similar calculation for B and C, and their Borda scores are 9 and 8 respectively. So the Borda winner from this preference profile is candidate A. Okay, how do I compute that? So this is M equals 3, right? And I claim that I can actually compute this with queries of size T equals 2. Okay, so obviously if you give T equals M, you can do anything you want. That's like having the whole table in front of you. With queries of size T equals 2, all you can do is something like this. Yeah, I just wanted to put a reference first that it's sort of a folklore result. We aren't the first people to realize that Borda count can be done with queries of size 2. We are the first to sort of give this more precise language in this query model and consider T greater than 2. So there is actually literature on our question for these so-called C2 rules, which are things computable with queries of size 2. But our paper is the first that really explores this and says what you can do with larger T as well. Okay, so how do you compute the Borda count with queries of size 2? So this is an example of a query of size 2. The algorithm submits as its query the set A and B, and it gets returned a complete distribution over preferences. This is also referred to in social choice as a preference profile. So I'd call this a restricted preference profile of how many voters prefer B over A versus A over B. Okay, and we can compute the Borda scores with respect to this restricted profile and see that A has 6 points and B has 3 points according to the Borda score. So I multiply this row by 1, this row by 0. Okay, so this was one query of size 2, and I can do the other ones as well. I can query A and C and compute the Borda scores of A versus C, and I can query B and C and compute the Borda scores of B and C. And now the magical thing happens that if I add up the Borda scores of A in both of these queries, 6 plus 4, look, it's 10. That was their Borda score in the original thing. And similarly, B, 3 plus 6 is 9, C, 5 plus 3 is 8. And so this is not a coincidence. This will always happen. If you add up the Borda scores in these restricted preference profiles, you will get the original Borda score from the original thing. And so this is a nice property. It's not actually that hard to prove. You can maybe see how the proof goes. And this shows that if you just query all the pairs of candidates, you can compute the Borda scores. So you can compute the Borda voting rule with queries of size 2 for any M. Okay, so that's great. There's a nice positive result by Borda count. Okay, so now I'm going to talk about a voting rule. It's something that's much harder to do. Okay, so Borda is easy from our perspective. And it turns out plurality is actually quite hard. And plurality is maybe the most important voting rule just because it's the most widely used. Select the candidates with the most number of first choice votes. That is the voting rule. Okay, and this is in very wide use today. Social choice theorists hate this rule because it has it's very poorly behaved in terms of the axiomatic properties it has, but it is in wide use. And we're going to give you another reason to hate this rule. It's not computable with queries of any size T less than M. So for any number of candidates at M, plurality cannot be computed with queries of size T strictly less than M. Okay, so and moreover, we can construct instances of this problem, so sort of query adversaries, where any algorithm making queries of size strictly less than M can only correctly output the plurality winner with probability at most 1 over M. So we're allowing an even randomized algorithm, and we're saying this randomized algorithm can't do better than just guessing one of the M candidates. That's what 1 over M is here. Okay, so how do we prove this? This is the one thing I'm going to sort of go through a bit of details about how this is proved. The rest of the talk, I'm not really going to talk about proofs at all. And the idea is to construct adversarial profiles where certain pairs of candidates are indistinguishable by queries of size T less than M. And the query adversary is going to respond to queries by sort of randomizing over these adversarial profiles. Okay, and so what do I mean by indistinguishable by queries of size T less than M? Okay, so here's an example for M equals 3 and T equals 2, trying to do a plurality winner. Okay, so this is a preference profile. This is a preference distribution. 25% of voters rank A, B, C, 25 rank A, C, B, etc. And so the interesting things to note about this is that if you look at just A and B, say you made a query to A and B, what would you get as your response? You see that these first two columns prefer A and these second two columns prefer B. Okay, so it's 50-50 split between A and B. And similarly, it's a 50-50 split between C and A, and from B and C as well. This column and this column prefer B, this column and this column prefer C. Okay, so the response to any query of size 2 is going to be a 50-50 split between the two candidates. So everything looks the same with respect to a query of size 2. So all the candidates are sort of indistinguishable by queries of size 2. Yet, there is a clear plurality winner here. A has the most number of first choice votes. So if you run the plurality voting rule on this instance, on this preference profile, this preference distribution, A should be the answer. And so this shows that an algorithm is going to run into trouble. Formally, we can consider the following adversary. With 1/3 chance, I'm going to answer queries with respect to this profile. And with 1/3 chance, I'm going to do it with this profile and this profile. And these ones are just the same thing, but I've permuted the labels of the candidates. And so from the queries, you're not going to be able to tell which one of these three is actually the one. So the best you're going to be able to do is guess and get right with probability 1/3. Okay, so that sort of proves the theorem in the case of m equals 3 and t equals 2. And now let me go into the general case. So the general case relies on the following lemma, so this doesn't completely prove the theorem. This is like the main key building block towards it. So it says there's this specific distribution that we can construct D over preferences M candidates with two special candidates A and B, such that A has a better plurality score than B, and restricted to any set of less than M candidates, D is invariant under exchanging A and B. So this doesn't say that all the candidates are the same and one is the plurality winner. This says that it's indistinguishable with respect to this pair of candidates. So if I just swapped this pair, then the answer should be swapping that pair, etc. And so this is sort of a weaker statement. But essentially the query adversary we're going to construct, which I won't go into those details, is just going to be a mixture of this specific distribution from this lemma with many different pairs of A and B chosen in specific ways. And so you can maybe imagine how this adversarial distribution would be useful as a building block. And that's the part of the proof I'm going to go through right now is how do you construct such a distribution with these two properties? Okay. So, so again, this is not like the previous example where all three things were indistinguishable and one of them had the highest plurality score. This is a weaker property. We just want these two things to be indistinguishable, and we just want them to have different plurality scores. From this, it's possible to build up this larger thing. Okay, so here is the distribution. It's going to be defined as the ranking output by the following algorithm. So I'm going to, this is sort of like a sampling algorithm for selecting a ranking over the M candidates. So I'm going to select some uniformly random subset S over all the candidates other than A and B. Okay, that's the first step of the algorithm. Everything not A and B, I choose whether to put it in S or not with a fair coin flip. Okay, then I'm going to define the partial ranking where I rank everything in S in some random order, and then A and B, and then everything not in S in some random order. So I've told you now everything about the ranking except whether A is greater than B. And the final step is to determine whether A should be greater than B. And I do that if and only if the cardinality of S is even. Okay, so on the right is an example of two possible outputs from this distribution. So if these two special candidates A and B, and say that the random set S happens to be this set containing E, G, and H, and they happen to be in this random order. Everything else is in some other random order. And then I see, okay, S has size 3, which is odd, so I put B above A. And in this other draw, we did the same thing, but we had an S that had even cardinality, so I put A above B. Okay, so these are sort of like typical outputs from this distribution. So this defines a distribution over rankings, and so I think of this as a preference profile. This is for every possible thing that could be output by this algorithm with a given weight, I have the corresponding weight of voters with that preference. So that's the definition of the distribution D. Okay, so I claim that it satisfies these two properties. One of them is quite easy to prove. The first property, that A is more first place votes than B. Okay, why is that the case? Well, when are one of A or B ever going to be near the top here? That's only going to happen when S is the empty set. And the empty set is even cardinality, so only A can possibly be at the top. Because the only way either of them gets to the top is if S is the empty set, in which case it's A, not B. Okay, so that's why A is a higher plurality score than B. Make sense? Okay. Okay, so the harder part, how do I show that this distribution is symmetric with respect to exchanging A and B when I restrict to any subset of size less than M? Okay, so how do I do that? So fix some set of candidates Q of size less than M. And how am I going to prove that D is symmetric when restricted to Q? Well, there's three cases depending on how Q intersects the set A, B. The first two are easy. If Q doesn't contain A or B, then what's D restricted to Q? That's just the uniform distribution over Q, basically, over orderings of Q. Okay, it's not hard to see that. And it doesn't mention A or B at all. This is obviously symmetric with respect to exchanging A and B. Okay, case two, say it contains one of the special candidates but not the other. Then D restricted to Q looks the same from X's perspective, whether X is the candidate A or X is the candidate B. Okay, it's in either case, it's so Q contains some candidate X from the set A, B, and not the other one. And what the distribution is I choose a random set of things to go above it, a random set of things to go below it, and that's it. There's no parity check at all. It's going to be the same whether it's A or B. This is going to be the same distribution. Okay, the hard part is what if Q contains both A and B? And it's not even that hard. Basically, what I'll say is here's an equivalent way of sampling from this distribution D, where I do this random set S, but restricted to Q. And I'm gonna do that by sampling random sets S1 from everything in Q except A and B, and S2 from everything not in Q. Okay, and remember, because Q has size less than M, this set Q complement is non-empty. Okay, there are some possible things here. This is where I use the assumption that my queried set has size less than M. Okay, and so that's like saying S is S1 union S2. I have the random subset of things within Q and the random subset of things without Q. And then what the algorithm is doing is I randomly order S1 above A and B and the things not in S1 below A and B. And then final step of the algorithm determining whether A is greater than B. Well, that's if S is even parity, which is the same thing as saying S2 has the same parity as S1. And because Q bar is a non-empty set, the parity of S2 is going to be equally likely to be even or odd. And so the key insight is, and again, this algorithm hasn't used S2 yet, so it's completely independent. So the key insight is ranking A above B is an independent event that happens with probability 1/2 when the Q has size less than M. So that means this, and now if you just look at this 1, 2, 3 description of this distribution, it's clear that there is no difference between the roles of A and B here. It's just going to be some independent thing, because I don't know about these things that weren't in S1. Okay, so it's okay if you weren't following that. We're gonna change gears now, and I'm going to talk about some other results. That was only proof I wanted to go through because I think it's a really cool construction. Yeah, so onward to other things now, unless there are any questions about this. Okay, so I've just now showed you proofs that plurality is doable with queries of size 2, and Borda is doable with queries of size 2. Plurality isn't doable with any query size less than M. Okay, what about other rules? And we're going to consider this family of scoring rules, which incorporates Borda and plurality and a bunch of other stuff. And it's basically just a vector. It's parameterized by some vector that says how many points you get for each position you are in a voter's ranking. Okay, so Borda gives M-1 points for the first candidate in the ranking, M-2 for the second, etc. Plurality just cares about the first one. So that's the vector 1 followed by a bunch of zeros. Okay, and what we do in our paper is we actually characterize for every scoring rule. We can tell, we have a nice characterization that'll tell you, given this vector, what is the query size that you need to compute it. And half of this work was actually done for us. If you look at this paper from Bentert and Skavron in 2020, they showed that, and again, this is phrased in a completely different language, and they sort of use something more similar to our noisy query model than the exact query model, but this is essentially shown in their paper that the following vectors, alpha 1 through alpha t, each admit a t computable scoring rule. Okay, and what is the vector? What is the jth vector of this kth vector of this family? It's the vector whose jth component is this binomial expression involving j, k, m, and t. Okay, so these are just some random vectors. I have pictures of these vectors on the next slide. You can see what some of them look like. Okay, so this is a collection of scoring rules that are computable with queries of size t for any t less than m. Okay, are there other ones we're missing? And so our paper actually showed that no, there's not. This is all of them. In fact, it's okay. One thing you can do is you can take linear combinations of these, and that'll also be a t-computable scoring rule. But that's it. So that's our theorem. It says that these vectors defined by Benter-Discoverin actually form a basis for the set of all scoring rules computable with queries of size t. Okay, so these are subspaces generated by these vectors. And so our result is sort of like a converse theorem of this prior work. They just showed that these are some things you can do, and we show that's all you can do, this and linear combinations of it. And there's a sort of pictorial representation of this space of scoring rules. And so here I've got, you know, I'm thinking about this subspace, and I'm making the normalization that the sum of all the components must be 1. That's you can make scoring rules are equivalent in terms of who they select as their winner. There's a bunch of normalizations you can do. This is one particularly nice one, I think. Makes it look nice, pictures. So we have this simplex of scoring rules. At the very top is plurality, 1, 0, 0, 0. The other corners are kind of silly ones. This is like select whoever has the most last place votes. It's a very bad voting rule to use. But okay, so that's the full space of all the things you can, all possible scoring rules. And then we have these subspaces of what you can do with queries of size 3, 2, and 1. Okay, so in the middle is kind of this trivial voting rule. It's not even really a voting rule. It just gives everyone equal score, so it doesn't actually like decide anything. Then we have with queries of size 2, as we've seen, we can do Borda. And essentially that's it. There's Borda, and then there's anti-Borda, which is selecting the person with the lowest Borda score. That's also computable with queries of size 2. And anything else, any sort of vector that's on a ray from the origin is equivalent as well. So there's really only, I could make another normalization and collapse this to a sphere around the center of the tetrahedron. But I think it looks nicer without doing that. So, you know, all these vectors along this line are the same as Borda, and all the vectors along this line are the same as anti-Borda. And then we have, okay, so then we have what you can do with queries of size 3. That's this subspace here. It's just this plane. It looks like a kite because it's just projected into a tetrahedron, but it really is a, you know, think of it as a two-dimensional subspace. And you get things like this. So like, you know, you can't compute plurality. That's not in this subspace with queries of size 3 when there are 4 candidates. But you can compute the thing that gives, you know, 3 points to the first choice vote and 1 point to the second choice vote, which is like almost plurality. So it's like, maybe that's even better than plurality. Maybe we should be using that instead. So, you know, there are some things you can do that are interesting here. So, and this is one of the basis vectors from Benter and Discoverin. Okay.
Sorry.
Yeah.
Okay. So computable basically means that you can implement the scoring rule or the voting function with query model, right?
Yeah. Yeah.
Okay, and so if I just draw different like subplane subspace or different line segments that across the central, they are all computable, right? According to your explanation.
No, I mean anything that's not in this red region, which is like this two-dimensional slice of this tetrahedron, is not computable with queries of size less than 4.
Okay, I see. So you should restrict to this red region instead of arbitrary two-dimensional. Okay.
Yeah, it's not any subspace. There's specific subspaces defined by this prior work. So we
I see.
are showing that this is exactly, there's these nested subspaces that are what you can do with these limited queries, and that's exactly it.
Okay.
Okay. Okay. I haven't talked at all about so this is just about computing a voting rule at all. This is what you can do if you have an unlimited number of queries. And now I want to ask the second question that I posed at the beginning, which is when you can compute a voting rule, how many queries do you need? Okay, so we're going to fix some M and T and again, we're just going to consider for this paper scoring rules. So take some scoring rule parameterized by a vector alpha, and I'm going to let T star be the minimal value such that alpha is an R of M T star. So that means that it's possible to compute this scoring rule with queries of size T star. And I assume that I'm given some query size T may be greater than T star. How many queries do I need to guarantee that I can come up with the winner according to the scoring? Okay, so an easy upper bound is the number of queries it needs to hit every set. And this has a name. It's called the covering number of M, T, and T star. It's just the number of subsets of size T needed to cover all subsets of size T star. Okay, so if I can do that, I've given the algorithm all the possible information it could want. And given that it's possible to execute the voting rule just from that information, this is obviously, this sort of brute force algorithm should do the trick. So if anything works, this works as a sort of naive upper bound, querying every possible subset of size T star. And then this is a sort of combinatorial problem, how you do that. The covering number grows something like M choose T star over T choose T star. And this is almost tight. There's results about this. And so you can think of it like this. This is really a lower bound on the covering number, but it's almost a tight bound. But again, this is only sort of an upper bound on, like, can an algorithm do something smarter than querying all subsets? And we actually give an adversarial construction showing that no, you can't. You actually do need exactly the covering number of queries. And what this boils down to is showing that we can have some query adversary where there is some specific subset of the candidates that an algorithm needs to query in order for it to learn any useful information. And so that basically implies that you do need to query this many times for deterministic algorithm to get the correct answer, because you might need to query, that might be the last subset that you query, right? So it is possible to like hide one specific subset, that if you query that, you'll learn who the winner is according to alpha, and if you don't query that, you'll never learn anything. So even an adaptive algorithm, if it's deterministic, can't do anything here. Okay, what about randomized? Well, a natural follow-up is, say that you can only make a delta fraction, cover a delta fraction of the subset. So you make delta times this approximation to the covering number. Then we show that algorithm can succeed with probability at most delta. And again, it's not exactly delta, it's delta plus a little bit. Okay, so there's a little gap here. This is an upper bound on the success that an algorithm can do, and we don't actually know that this is a tight lower bound at all. And just to give you an example of the sort of gap between our knowledge of upper bounds and lower bounds, let's look at the very simplest possible case, which is border count with m equals 3. Okay, so here we know border count can be done with queries of size 2, and suppose there's 3 candidates. What is the best a randomized algorithm can do in terms of the fraction of the 3 queries it's allowed to make? So there's only 3 possible queries this algorithm can make: A and B, B and C, and C and A. And given on the x-axis whether it makes 0, a third, 2/3, or 1 of those queries, this is the upper bound from that previous theorem about the probability it will find the correct winner. And the naive lower bound we get is just 1 over m. It's always allowed to just guess 1/3. And so there's a gap between these, obviously. And it turns out the truth is this. And so we worked out for this easiest possible case, what is the optimal algorithm here? If you have 0 queries, you can't do better than guessing. If you have all the queries, obviously you can get it with probability 1. And in between, it's surprisingly, actually, it's strictly in between our upper bound and the naive lower bound. And yeah, I don't think I'll say much more about it. There's pages of proofs devoted to nailing down this point here. For when you can make 2 queries, the optimal algorithm is quite complicated, and the algorithm is even, and the adversary that shows the lower bound is quite even more complicated. The algorithm is basically to use 2 queries to learn the border score of 1 random candidate, and then if it looks better than average, select it. Otherwise, select one of the other ones. And I won't say anything more about the adversary in that, other than it uses Fibonacci numbers. So go read the appendix proof if you're interested in that. I don't have time to talk about it. And this is all just to say, this is a sort of interesting question for future work. We don't know what the optimal strategy for an algorithm is. The optimal algorithms can be really weird here. In the sort of fine-grained sense. In the coarse-grained sense, we think we have a pretty good handle on how good a randomized algorithm can do. And for deterministic, the book is closed completely. Okay, so that's all for rank preferences. I only have like 20 minutes left, which is fine. I was planning on spending most of the time on ranked setting because I think that's the more fundamental social choice theory problem. But for the rest of the talk, if there are no questions, I want to say a little bit about this prior work about approval ballots, because it's very interesting, and there's some nice contrast with what you can and can't do in that setting. Okay, so again, back to this picture. of how polls worked. They're not shown a set of candidates and have to rank them. They're shown a set of comments and have to say whether they approve or disapprove of the comments. So the input is this incomplete approval matrix, as it's called. And the output is a set of comments that they want to curate and say these are representative of the population. And so this maps nicely onto a problem in social choice theory called the committee selection problem, where the input is this approval matrix, who approves of what voter approves of what candidate, in other words, what user approves of which comment, and the output is a set of K candidates, in other words, K comments that you're going to show as a representative of society. Okay, naive thing you might want to do is select the K candidates with the most number of approval votes. And I'm not talking about incomplete information. I'm just talking about the classic setting for this slide. That's the sort of naive thing you might want to do. And it turns out that has some pretty bad axiomatic properties. In that if there's some like tight coalition that has say more than 50% of the voters, and they say we like this narrow set of candidates, you're going to get a committee that's not really representative of society. So there's these axioms that are meant to say that different groups that have aligned preferences each deserve representation. And the two most basic ones are this is the easiest axiom. It's called justified representation, or JR, and says that in the committee that you select, any subset of size 1/k of the population who can agree on at least one candidate. So it can't just be an arbitrary disparate set. It has to be like some cohesive set, it's called. They all like agree on at least one person. They should have at least one voter who approves of one candidate on the committee. Okay, so it sounds like a very weak axiom. This is the sort of weakest axiom of this hierarchy that's often studied. Okay, and you really should satisfy it because it's so weak. And then there's the extended justified representation, EJR, which is the same thing, except it's extended, it's stronger, which says that for any number L, any subset of L/K of the population who can agree on at least L candidates should have some voter who approves L candidates on the committee. Okay, so it's the same thing plugging in. If you plug in L equals 1, you get JR. So EJR is a strictly stronger notion that cares about larger groups of the population approving of larger sets of candidates. And so again, this slide is just reviewing classic what's known in this committee selection problem. It's known that a committee satisfying EJR, and thus JR as well, always exists and can be found in polynomial time. Okay, so what we want to ask now, say that this is all, if you have the complete approval matrix in front of you, say that you don't, and you have to query voters with small subsets T, what can you do to satisfy these axioms? Okay, so the first observation is that we can take one of the classic algorithms that's known in this committee selection literature, which is called proportional approval voting, and we can implement it with queries of size K, which is great. And so in this setting, K is the number of comments we want to output, vastly smaller than M. M is grows with the number of users. Anyone can submit a comment. Think of M as some huge number. Think of K as some small constant. And so this is great that we can actually compute this with queries of size K. Whereas in the ranked preference setting, so to do something like plurality or one of these generic scoring rules, we need queries of size M. Here we only need queries of size K to satisfy JR. And in fact, satisfy EJR. Okay, and what is proportional approval voting? It selects some committee C, maximizing the average voter utility for the following utility function. The utility of a voter for this committee C is the sum from J equals 1 to the number of approved candidates on that committee of 1/J. So if a voter approves of one candidate, their utility, we call their utility 1. If a voter approves of two candidates, we call their utility 1 plus a half, which is 3 halves, etc. Okay, you can, and so basically this gives you a way of scoring committee, and you can compute the PAV score using queries of size K. That's only asking about preferences restricted to that committee of size K. So if I take all the committees, every possible subset of size K, I make that query. This is sort of like M to the K algorithm. That's unreasonable size. That'll take too long in practice, but it is polynomial time. This gives me I can satisfy EJR with this algorithm. Okay, but as I said, M to the K is not great. We do show that actually you can do this with queries of size. So this algorithm requires queries of size T equals K. We show that you can actually do this with 2/3 K. So that's a slight improvement. It gives you a slightly improved runtime too, because it's this T. This is a naive algorithm. We're going to create every subset of size T. And so it's still kind of a bad runtime when m is going to be very large, and t, even if it's a constant, this is still like m squared might be too large, in fact. Okay. And again, this is a non-adaptive algorithm. This is just querying every this is querying this first algorithm I mentioned is querying every subset. This one is querying some more specially chosen subsets of size k, or of size less than k, in fact. Okay, in terms of lower bounds, for a non-adaptive algorithm, we can show that for any k greater than 2, we do need queries of size at least 2 to guarantee JR. Moreover, you have to query every subset of size 2. So you're going to need m squared queries. And this m squared is very interesting because we're going to see in a couple slides that for a non-adaptive algorithm, you can actually do this in linear and m. For an adaptive algorithm. So this lower bound only applies against non-adaptive algorithms. And we can push this technique further and replace these numbers. For any k greater than 72, we need queries of size t equals 11. And then that gives us also an m to the 11th lower bound. Okay, so that's the result. And I want to say a couple things about these results. There is a similar sort of like fun construction of these adversarial instances. Okay, and so here's one of them. So in this picture, every one of these circles is a candidate, and one of the ovals is a equal-sized set of the population that approves of all of the candidates inside the circle. Okay, inside the oval. So in this example, suppose we want to select a committee of size 2, but we only have queries of size 1, which are not going to be very helpful for us. They just say, what is the approval score of each candidate? Well, I claim to satisfy JR, I better select as one of the two candidates, candidate 1. Why is that? Because, as I said, these are equal. These ovals represent equal-sized populations, equal-sized subsets of the population. So the green subset is a cohesive set. They are a 1 over k of the population, because k is 2, is half the population, and they all have this guy 1 in common. So if I don't select 1, I violate JR. Okay, no one in this set is going to be happy if I don't select candidate 1. Okay, so I have to select candidate 1, but I only get to select 2 out of these 3. And with queries of size 1, these all look the same. If I make a query of size 1 to candidate 1, I see half the people approve candidate 1. Half the people approve candidate 2, half the people can approve candidate 3. I don't have any information about how these overlap to know that I should select 1 as one of the candidates, so the algorithm might make a mistake and get 2 and 3. So it can't be correct with, it can't always be correct, and we can push this higher and say it's actually correct with very small probability as I increase k. Okay. How do I do this similar lower bound for, so this is actually what gives us the first statement that I said about, you need m squared queries of size 2 at least. And we can push this further, in fact. And so here's sort of the next simplest example where now this was a lower bound against queries of size 1. Now I want to do a lower bound against queries of size 2. And for this, we need to make k equal to 6. Okay, and so this is another fun example. Okay, k is 6, and there's 7 candidates. So I'm going to be able to select 6 out of 7 of these. And I claim that to satisfy JR, I have to select candidate 1. So similar as the previous example. And why is that? Okay, so I'll just you can verify these claims offline. I will say there are 18 of these regions. Each represent equal size population. 3 of them just include 1. So 3/18ths of the population, which is 1/6, just approve candidate 1. K is 6. So to satisfy JR, I have to select candidate 1. 1 over k the population, just want 1. JR says I have to select 1. And now I want to claim that all these candidates are indistinguishable. So with probability 1/7, I'm going to miss candidate 1, and then I will fail JR if I only have queries of size 2. And so why are they indistinguishable? You can stare at this and verify that this particular instance has the following properties. First, every candidate is in exactly 6 of these 18 circles. And second, every pair of candidates is in exactly 2 of the 18 approval sets. Okay, and that means that if I have queries of size 2, it's going to look the same no matter what pair of candidates I choose. These 2 bullet points say that a query of size 2 doesn't give me any information. So similar sort of counterexamples. Okay, yeah, so that's it for yeah, I want to leave a bit of time for questions, so I'm going to go quickly through the last couple slides in the next 4 minutes maybe. But so this is a sort of lower bounds against queries of size 2. We ran a computer search to find lower bounds for larger query size, and for each one of these we need larger k. So that's this 72 requires t of size at least 11, came from this table. An interesting open question is we couldn't actually prove that as k increases, we need higher t. For all we know, there could be some constant where this table stops, and that's a sort of interesting open question. I'll mention at the end again. Okay, adaptive algorithms. I'll skip this slide. The main takeaway, I just want to say the main result of our paper was actually this 2023 paper was that we can guarantee AGR in O of m k squared log k adaptive queries of size k. And we do that by finding a committee that locally maximizes PAV score. You don't need to find the global maximum, you just need to find a local maximum. And we show that we can do this with this many queries and of only size t equals k. And we actually empirically tried to evaluate this algorithm on some pseudo-synthetic data, where we took comments from a discussion on Reddit, from actually multiple discussions put together to make an interesting ensemble of characteristics, because people, approve or disapprove, like or don't like comments on Reddit. And we ran this on this data set, and I won't go into any details about all the choices that were made here. What this is showing is on the x-axis are a number of comments, and on the y-axis are the number of voters who approved of at least n comments on the committee that our algorithm output. Okay, so and we do this for a few different algorithms. AV stands for approval voting. That's the naive thing I mentioned before, where we just take the ones that are satisfied most number of votes. The blue and the green are various implementations of our algorithm in the noisy query model. And the main takeaway is that these algorithms are more representative than approval voting. Even though approval voting succeeds in having a lot of people who have like 10 candidates approved, 9 candidates approved, our algorithm succeeds more on this lower end of just making sure it's inclusive and everyone has at least a small number of comments that they approve on the committee. Okay, so this is my final slide. Just to summarize to go back to this, I've shown you 2 different models. They both have this aspect of there's queries. You get something about a restricted set, but it's in 2 different. Each paper was in a completely different context, and they're both classic settings in social choice theory. And the first part I talked about was ordinal votes. We're selecting one winner, and our objective is to implement some scoring rule. One result I didn't talk about is we also have similar lower bounds against STV. That's the single transferable voting rule. In the United States, at least, this also goes by the horrible name of ranked choice voting, which is very non-descriptive. And it's also another popular one. We also show that there's the same sort of negative results about that as with plurality. And then the other context was approval votes with K winners, and we want to satisfy things like JR and EJR. So as for the information theoretic, how many queries, what's the query size that you need given unlimited queries? The results are very negative in the ranking setting, in that you need queries of size M, except to do some very special scoring rules like Borda. And in the general case, we can satisfy EJR with queries of size K, which again is much better. K is much smaller compared to M in the context that we care about, that we're trying to model. In both cases, we have very strong results against non-adaptive algorithms, that a non-adaptive algorithm must query all subsets before it can do anything interesting. And in the ranking setting, we can even extend to adaptive algorithm lower bounds, because these query responses essentially don't tell you anything at all. Versus as in the approval setting, we actually do have efficient algorithms that use a small number of queries because you are learning things with these queries. So these 2 settings have some interesting different characteristics in terms of these query models. So there are a couple open technical questions I just want to recapitulate. First was this one about nailing down what is the best randomized algorithm in terms of trying to maximize success probability. Totally wide open. We have no techniques to prove anything about that. So maybe that's an interesting thing to look at for future work. I think it's a very hard question. I'm not going to be working on it anytime soon. The other one that is really nagging me from this project from 2023 is that we had this we had these lower bounds against queries of size 1, 2, 3, all the way up to 11, and these were all the way up to 10. I mean, and these were just output by solving these linear programs. We don't actually know that. We don't have a general construction that says for any fixed t there is a K such that you can't satisfy JR with a non-adaptive algorithm with queries of size less than that. So I think that's a really cool open question. We couldn't come up with any sort of general construction like we were in the case for rankings for lower bounding plurality. And then finally, an open-ended question is maybe there's other types of queries we should be considering here. And I think this is kind of interesting because, plurality, as hated as it is in social choice theory, a nice property it has is that people often say it's a simple rule. You just have to ask voters to put down one thing, not a complete ranking. And in that case, the sort of complexity you'd think of plurality from limited queries, like I've talked about this result, my collaborators have as well with people who do social choice theory, and they say, but plurality is easy. This is just a bad model then. And I wouldn't say it's bad. It's an alternative model. It gives you, like, in a context where picking one thing out is hard, but comparing a small number of things is easy, then plurality is hard. That's the main takeaway from this. But there's natural, interesting follow-up questions like, say I give you a combination of those. Say a query can be compare some small number of things or pick one thing out as your favorite. Then, that gives you a more powerful set of queries you can perform. Maybe there are more things you can implement with that, and that would be more maybe realistic. And I will note one other paper that was also in EC 2024 this year with some overlapping co-authors, Manuel Wuthrich and my advisor, Ariel Procacia. And it sort of applied a similar sort of querying framework to LLMs, where an LLM they think of as a tool to generate new statements that people might approve of. And they sort of study the axioms of, say you have some AI large language model that's able to come up with a query that has agreement on, and then they sort of integrate this into this query model and say, what are the things you can do with such a powerful black box? And they try to empirically test this as well. It's a very fascinating paper. You should all take a look at that. Okay, that's all for me. I'm happy to take any questions.
Okay, thanks for the talk. Are there any questions?
Can I ask a question? Can you hear me?
Yes.
All right, thanks for a very exciting talk. I have probably a stupid question. Instead of the query complexity, another thing you can care about is the computational complexity. So my question is, when you prove a query complexity upper bounds, does the algorithm always have the computational complexity that's, say, polynomial in the number of queries that you make?
I see. Well, okay, for the results that I talked about today, there are very few positive results. One was this algorithm that we actually implemented. So yes, this one was polynomial time. And for the sort of for the positive results like Borda and the scoring rules that come down with small queries, those happen to also be in polynomial time. I don't know of any sort of grand theorem that would say that just because you use small queries, you're going to be efficient as well in terms of actual runtime. But certainly all the positive results that I've presented do have that property.
I see. So for the first part, you give like very complete characterization for the query complexity upper bound, right? So all this algorithm has like a polynomial time algorithm, right?
Yes, for the subspaces of the scoring rules, all things I said can be done with small queries. Yeah, can be done efficiently.
Thank you. Yeah.
And it's kind of for the ranking, these algorithms are not really smart. You kind of have to query all subsets of size t still. And so it's like, yeah, you're aggregating, you're doing a simple algorithm on all subsets of size t. So that's why the runtime happens to be the same as the query complexity. It's not really doing anything hard on top of the queries it receives.
I see.
Okay, are there any other questions? Maybe I can ask one or two. The first is, have you considered some pack learnability version of these problems? Like, you can just passively get samples from the underlying distributions.
Yeah, and so that's sort of what I was talking about with the noisy query model at the beginning, where you get empirical samples. And I didn't talk about it in this paper, but in this talk. But yeah, we have results on that, and there's nothing really surprising there. It's a sort of classic bounds you get from these sorts of problems.
Okay.
Yeah.
Yeah, and have you considered like yeah, I saw this paper generative social choice and also attend talk, but I'm wondering if you are considering like linking the your results to like some to the fine-tuning or training of LLMs, like because they also need to aggregate preferences from pairwise comparisons, right? And generate or aggregate a preference of agents or humans or users or human learners, and then put them as input to train the LLM that more fits the
I think people are thinking about this. I mean, I know there's a ton of interest in LLMs from all my social choice theory calls right now, and people in my lab. I personally do not really participate in that literature, so I'm not the right person to ask that question.
Okay, I see. Okay, thank you. Okay.
Yeah.
Okay, thank you. Okay, thanks again for your wonderful talk. If the audience have any further questions, feel free to email Jamie and discuss
please.
with them. Yeah, thank you.